Hi everyone, welcome. Do feel free to say hi if you're just joining. It'd be great to hear from everyone. I hope you're keeping well. I hope you're having a good weekend. And we're getting to that point now. We're coming up to exam time. And I'm sure many of you in year 13 are kind of finishing the courses. And those of you in year 12 as well, I can imagine have had quite a big term and quite a full on in terms of the A-level content. Be lovely to hear from you. Do feel free to say hi in the chat, share answers and ask questions as we go. We're looking at trigonometry today, so it's quite a big one. Solving trig equations is probably one of those, welcome Esme, hi, one of those big topics that I think, certainly for me, was something that was very new for A-level, so it's a really good one to look through. So we're looking at trigonometry, we're looking at solving trig equations. It'd be great to hear from people, as I said. Do feel free to say hello if you haven't already, and I'll see that in the chat. Thank you for joining so promptly as well. Hi, welcome guys. Hi everyone. Cool. So as I said, we're going to be looking at solving trig equations today, which is a big A-level topic that extends throughout the pure maths into year 13. And to be honest, actually comes up a little bit in mechanics as well. Welcome. Hi everyone. Cool. So I'm going to get sharing the slides and get started on this topic. But welcome, as I said, do feel free to ask any questions as we go. So to start with, it will be like the year 12 AS content, and then it will build, as I said, it's one of those topics that's crucial for both. So predominantly, we're going to use the trig identities we see in year 12. Yeah, no worries. Right, so I'm going to share my screen now, and hopefully you guys will be able to see this, and I'll give us a little overview of exactly what we're going to be covering today. So hopefully everyone can see that, but I can still see the chat. So any questions, comments, answers you want to share, that'll be brilliant. And we'll kind of power through this content together today. So welcome if you've just joined, do feel free to say hello. Lovely to see so many people here. And yeah, well done as well for motivating yourself to join in on a Sunday. It's lovely to see so many people taking part. So well done. Right, so we're going to get started. We're going to look at solving trig equations. And I'm Max. So if you've been to one of these classes before, apologies, you might have heard me say this before, but I'm head of maths at Snap Revise, and I've been teaching A-level maths for the last 4 or 5 years, which has been quite an interesting time to be doing that. And GCSE and below as well. So it's been nice to see how the A-levels changed and also look at what content is really focused on in exams. So that's a bit about me. What I did also want to say, and I'll talk about this a little bit later, is you may be aware that there's A-level crash courses, seminars coming up in the Easter holidays that are kind of perfectly tailored towards really the advanced information in mind and looking at the kind of summer exams and hoping to prepare you guys for that. So I'll talk a bit more about this towards the end because we're kind of in a unique position this year with information coming through about the exams that's a bit more specific in comparison to the information we normally have. So we've geared these crash courses and seminars up to kind of target that. So I'll talk about that towards the end, but we're going to get cracking with the trig stuff. So what we're going to look at today is deduce the angles at which trig functions give negative values, solve equations for trig functions given like a specified domain, and look at using identities and quadratics to solve the harder trig equations. So I know personally for me at A-level, this was very much a new topic, and there were so many little subtleties that you have to make sure you completely get or you can iron out. Otherwise, it just feels like the topic's quite confusing. So we're going to work through this very carefully. Do feel free to share answers and ask questions as we go. And thank you again for taking part. Do say hi if you haven't already. I can see the chat, so hopefully I'll be able to see comments and questions coming through. Okay, right, so to start with, in terms of prior knowledge, what we should be good with are the trig graphs. We're definitely going to need to be absolutely happy with how they look. So I'm going to start with the sine graph, which has a maximum at 1, a minimum at -1. And I'm just drawing it for the kind of specified domain of 0 to 360. But hopefully you guys are happy that that can continue kind of as an infinite wave as well. Is everyone absolutely happy with that? Are we happy with that general setup, confident in sketching the sine graph, do let me know. Right, the next bit, cosine, the cos graph, here is going to be a translation of that. It's basically just a shift of the sine graph. They behave in a very sort of similar way. I'm going to just try and sketch this as best as I can. Okay, again, maximums and minimums at 1 and -1. Superb. Right, excellent. Now, tan is the kind of interesting one, and we'll see why in a second when we sort of look at the identities. It has what we call, does anyone know what we call these lines? These kind of infinitely approaching but never touching lines that it has. So it has these lines at 90 and it sort of repeats every 180 degrees. Yeah, excellent. We call them asymptotes. And there's other graphs where we see asymptotes as well, which are kind of like discontinuities where the graph sort of breaks for that value. Yeah, absolutely. And yeah, it's a cool word, isn't it? So asymptotes, so tan does behave a little bit differently. And we'll see that in a second with the two main trig identities we use in year 12. We have kind of another couple of identities we have in year 13 as well, but they stem from these two. So they actually come from the ones we use in year 12. So hopefully we're happy with the two main trig identities we use in year 12. Our sine squared plus cos squared is 1, is identically equal to 1. So if we put the same value into sine and cos, we square each of them and we sum them, it will always equal 1. So that's one of the identities. And the other trig identity is that tan theta is identically equal to sine theta divided by cosine of theta. Now, this is actually why tan has the asymptotes. It has little breaks in the graph, because you guys all know from calculator error, whenever you try and divide by 0, there'll be a problem. So if you look at 90 and 270 on the cos graph, cos is equal to 0 there. So we're trying to divide by 0, which isn't possible. And that's why we have these asymptotes on the tan graph. So these two identities we need to be absolutely happy with. Are you guys happy with those? Have we all seen these before? If not, they're going to be very important for year 12, but also for year 13, pure maths. So please make sure you know those. And we're going to see them kind of as a recurring theme today as well. Brilliant. But I'm going to move us on so we can actually start doing some problems here. Lovely. Excellent. Right, that's good. So this, whether you're doing AQA, Edexcel or OCR, I can't stress how important this topic is. This will be on all the boards and it will be in a lot of depth in the same sort of way. As of since 2017, I personally think the A-levels have become a lot closer together in terms of the different boards. The content is very much the same in terms of the pure, the trig certainly as well. So this topic is useful for everyone, whatever board you're working with. So trig functions in the unit circle, I'll just briefly kind of explain this. Some people learn like a cast diagram. I'd be interested if you could just give me a yes or a no if you've done that before. I know some students don't like it and other students really always use it. I find it quite useful to save me drawing out all the different graphs, but just a yes or no if you've used a cast diagram before. No worries. So the way it works is if you take the angle with the positive x-axis as theta, it tells you which kind of quadrants, if you work around in an anti-clockwise fashion, whether that function is positive or negative there. So if we imagine this is 0, this is 90 degrees, this is 180. And I will be completely honest with you, I really didn't like it when I first learned it because I don't think I spent enough time looking at it. And then as the course went on, I found that in year 13, I used it a lot more. If you like using the graphs, you've got a kind of way of working through that. That's great. I'll talk it through briefly. Some people learn it by using the graphs and they solve trig equations using the graphs. Absolutely fine, whatever works for you. The main thing is with these trig equations is that we don't lose solutions, that we pick up all the different solutions where possible. So the way that the kind of unit circle or cast diagram method would work, that hypotenuse was sort of 1, because it's a unit circle. Is everyone happy that on this sort of setup, if that length was 1, then the distance across the x would be the adjacent, and we've got the hypotenuse as 1. So this would just be cos theta, and this would be sine theta, because from like sort of SOHCAHTOA. So this, just as a kind of step back for a minute, even if you don't like casts, or whether you do, this is quite useful, because what it also does is it also proves the identity. Cos squared plus sine squared is 1 from Pythagoras. And it puts a lot of ideas together. So as you move around, that will give you that value. And what we'll notice is that in this kind of quadrant here, for obtuse angles, if we put the line in here, sine would still be positive, but cos and tan would be negative. So it tells you what kind of the functions are doing for different parts of the graph. So if we look at this one at 90 degrees to 180 degrees, the cos graph is negative. The sine graph, though, is positive. And that's what this is showing from 90 to 180. The only function that's positive in there is the sine graph. Cos and tan are both negative. So what we'll do, we'll see this a little bit in more depth, but the other thing that it allows us to do is look at the symmetries. So those of you that have learned to solve trig equations using the graphs, I know you're probably used to saying, right, if I look at this bit here, say this is 60, I know that for the cos graph, that's the same as if I moved 30 on this way. Do you guys, is that the way some of you guys work out? You use the sort of symmetries in the graph and say, right, so 60 would be the same as if I had 270 and I add 30 on and I get 300. That would come out as the same value. Yes, exactly. Yeah. So there's all these different rules you can learn as well. And to be honest, the more confident I got with the cast diagrams, the less I used those rules. But effectively using the graphs is using those rules as well, because you sort of looking visually at the symmetries. What we find is it can just be a bit tedious to draw the graphs out, but some people do really like learning rules and drawing out the graphs, which is absolutely fine. Yeah. Yes. So sine is positive from 0 round to 180. Sine is not positive after 180, between 180 and 360. Sine is not positive round here. Okay. And likewise, if you went the negative direction from 0 to minus 180, sine would be negative. No, so I don't think you need to necessarily know all these rules by heart if you can spot them from the graphs. I don't personally learn them all off, because if that helps you, you absolutely can, and it's sort of good to be aware of them. But you can kind of see this from the symmetries in the graphs. So I'm just writing a couple of them out, which you may well recognize. And I think some of the textbooks do test this, but really the likelihood in an exam of just being tested on these rules, I think, is quite low. It's more going to be the implication of if you know them through the solving and whatever technique you use. So what we'll do, we'll see how this is useful in a minute. I'm going to just move this on. So for example here, we know that trig functions are periodic, meaning that the trig equations have infinitely many solutions. So they have infinite solutions, and that's why we specify a domain. So infinite solutions, or many solutions for a given domain. So that's actually really important, that they sort of always tell us what values, where we're looking between, like 0 and 360, quite a typical one. Guys, do feel free to, if you've done this before, solve this. We'll do it using the graph method, but I may also reference cast for those that want to see how this would work. So the first step is actually find the principal value, find the first value using your calculator. So find the first value as you would have done. Brilliant, well done if you've done this. Find first value with calculator. Excellent, and thank you guys, do feel free to share, check you agree with each other as well. So we're going to do theta, we do inverse cos, arc cos of both sides of root 3 over 2. It may also be one that you know or you recognize as one of those sort of special exact values, and that will be 30 degrees. So what this is showing me graphically and I'm obviously doing this very roughly to scale, is that if you put 30 into the cosine function, it would spit out √3/2, which is just a bit less than 1. Now, using your graph and your knowledge of the cos graph, you could go across and say, well, that distance from 30 to 90 is the same as this distance from 100. That's what I'm doing here. Let's try that again. From 270 onwards. So you could add 60 to there and get 330. And equally, you could say, well, if that bit is 0 to 30, it's 30 back from 360. And absolutely, that would allow you to get your other value. Yeah, superb. So the second part of the method would be to find the other values with the graphs. Brilliant. Now, this technique is absolutely fine. This is great. And if you're confident doing that, that's brilliant. We know that these questions can be harder than this, but well done if you're happy with that. So find the other values with, let's have a little look. Yeah, with the graph. That's great. Yes, yeah. And so then what you have to do finally is write down all the solutions, because there will be multiple answers. So you write down all the solutions. So you would say theta equals 30 and 330. Both those values, solve it. Okay, so in terms of the cast diagram, how that would have worked, I'm kind of running out of space here, but I'll just quickly reference it and we might see it in a minute. But what we would have is if we had S, A, T, C, and we know the first value is 30, and it's cos, and cos is positive because it's positive √3/2. Cos is also positive here. So that's 360 minus the same amount. So that's 30 and that's 330. Okay, did everyone get that about the cast diagram? I know I kind of crammed it in just very quickly there, but we looked at where it's positive. The graph, there were two ways you could have used this graph to get the other value. You could have noticed that this bit is like kind of symmetric to this bit because it's at a peak here and it's at a peak here. And I know that that's 30 degrees, that's 30 away from 0. So it's the same as 30 back from 360, which would be 330. So you could have done it that way, or equivalently, you could have done it as 60 away from 90. So it needs to be 60 away from 270, which would also land you up at 330. So hopefully that makes sense, but please do let me know if that still is unclear. Yeah, now, if you were to use the cast diagram, which I'm just going to do, I think I want to just give myself a bit of space here maybe to do that. So the other way is if you use the cast diagram, which tells us where the different functions are positive, we work from 0 in a clockwise fashion. We're going forward with the angles round to 360. The calculator's given me the first one as 30. Now, you know that we're dealing with cosine and it's a positive number. It's positive √3/2. No worries, that's okay. And if you don't like it, then just stick with what makes sense. I do want to talk it through though, because it can be useful in future. So I'm just going to explain this. All it tells you, it's more useful than just this going forward. So that's why I do want it to sort of speak it through quickly. It tells you where the different functions are positive. Is everyone happy √3/2 is positive? So cos is giving a positive output. So all you literally do is go, where would my other value be? Well, cos is positive here. This is the value my calculator gave me. So that's where I draw the first line. So where else is cos positive? In here. And so we use symmetries on here as well, that cos is positive in here. And this is like 270 if you're working around in a clockwise sense. So this is like the same angle back from 360. So this would be 330 if you took away, if you went this way. Or you could think of it in this direction. it's like 270, add this 60 bit on. So you get your two values as 30 and 330. Because that's right. So I know it's positive there because all you need to learn off by heart is SATC. That's how you write the cast diagram out. If you just learn these letters in that way, you know where it's positive or negative. So it goes, so do you see that on the actual cos graph, the graph is above 0 between 0 and 90, it's a positive number, and it's above 0 between 270 and 360. So the cast diagram is telling us that, but it does it for all three functions at once. It tells you for obtuse angles, this one is going to be positive, this one's going to be negative. But you could have done that just from the graph. You could have drawn the graphs out if you're confident with the graphs and seen where they're positive or negative. But this cast diagram just puts all the different functions in one. Cos was negative. Very good question. Excellent, Zach. So if cos was negative, what you would find is when you did it in your calculator, the principal value would probably come out as a minus number. So, or an obtuse value. So your first value would actually be in there and your other value would be in here, because in these two, cos would be negative. That was a brilliant question. So then your first value that your calculator would give you would not be in the all section, it would be an obtuse number if cos was negative. And you'd know, right, cos is negative where it's not positive, so it would be in here and here. And then you could go, so whatever that is, you take it back from 360, and that's how you could use that for a question like that one, Zach. But we'll go forward, and if you guys prefer using the graphs, absolutely fine. This is why I stressed at the start that it's so important you at least know how to sketch all the graphs, because we need some sort of technique that we can look at where they repeat. Exactly, good. So then you'd go 150 back from 360 to get the other value. A represents all. So all the functions from 0 to 90 are positive. Any acute angles, sine, cos, and tan are all positive. Great questions. Yeah, so you'd have to split the question up into sort of two bits. You'd have to go right for the positive bit and the negative, and we'll see that going forward. So let's have a little look at this one. So this one is a bit more involved. Oh, sorry, let me just try this. And do feel free to try it without me, but this one is a bit more work. So when solving a trig equation with an input of the form a theta plus b, we have to actually adjust the domain, adjust the interval we're looking at, adjust the interval before yes, from the original equation, yeah. So this is positive, isn't it? This is where cosine, sine is positive. Yeah, good question. So adjust the interval before using the inverse function. Okay, so what we've got is if I'm looking for between minus 180 and 180 for theta, no worries, brilliant question. What I'm going to do is I'm going to say, right, I'm looking for 2 theta plus 25. What we would need to do here is we would need to go, right, if theta is between minus 180 and 180, 2 theta would be between 360 minus 360 and 360. And so 2 theta plus 25 would be between, I've got to add 25 on, so minus 335 and 385. Okay, has everyone seen this before? That we have to adjust the interval. So we kind of need to effectively extend our search so that when we minus 25 off and divide it by 2, we've got all the solutions. Great, this is really, really important. So again, that's the first step. The second step is just what we're going to do. Use the calculator to find the first value, the principal value. So do feel free to do that for me for sine inverse of 0.2. And so what do we get? So shift sine, arc sine of 0.2, the principal value it's going to spit out is what? What do we get for that one? Let's check we all agree. 11.5, yeah. Good. So we've effectively found the first value for 2 theta plus 25. Now, what a lot of people want to do is instantly take away 25 and half it. We don't. We want to actually continue finding all the different values for 2 theta plus 25. Then to all of them, take off the 25 and half them. Okay, so what I would do, if you're using the graph, you're going to look from 335 minus 335 up to 385. And we've just found that the first value is 11.5. And we know there's going to be another one there, potentially another one there, another one there, and the one here might just be out of range. So what we do is we find the other values. Okay, so what you could do is you could go, right, if that's 11.5, if everyone's happy, that's 90 and that's 180. It's 180 minus 11.5 would get you this one. Oh, okay. Yeah, so this is sort of the year 12 stuff, you wouldn't generally have that. But I think, as people have mentioned, it's sort of scaffolded. That was a really good question. We'd have to have a little look more at those questions going forward, but I'll talk about that maybe towards the end, because we're going to see some of the quadratic and the disguised ones as well. But there are definitely key things to look out for. Really good question. Right. So hopefully we're happy that you can go, okay, so the other value is going to be 180 minus 11.5. Yeah. Then the next one is going to be 360 plus 11.5, which is still in range. And then this one here is like minus 180 plus 11.5. Sorry, minus 11.5, which is minus 191.5. Is everyone happy with what I'm doing at the moment? Because what I'll do, I will do it the cast method as well to check we're all okay. And then I get minus 348.5, which is out of range. Okay, so these are your other values. Yeah, is everyone happy with how I've done this from the graph? So that's my principal one, that's my second one, that's my third one. And then we went back and found that. And this one was out of range. Okay, so you find the other values. And these values are all for 2 theta plus 25. This one here is minus 180. So it's like 11.5 back from there. If you can see the sort of symmetry. You could think of it as well as this value take away 360. It would get you to the same place. Okay, good. Right, now that's how you get the values for 2 theta plus 25. We are going to have to adjust them all, which I'll do in a minute. But what I want to do before I do that is just explain on a cast diagram how you could do it. Now, on a cast diagram, and I will bring those answers back up, don't worry, is that we've got S, A, T, C. We're dealing with sine being sine was 0.2, so it was positive. The first value was 11.5. So by the symmetries, sine is positive in here and in here. So your next one here is like 11.5 back from 180. And that's where you'll hit that again. And then you'll also hit it back round here 11.5 on from 360. That's where you get your 371.5. No worries. And then also in the negative direction, you'd also hit it 180, minus 180, minus 11.5. And you'd try this one, but it would be out of range. So that's where you get your free values. So there's our values we get for, and actually this is 2 theta plus 25. So what we need to do now is if 2 theta plus 25 can be all of those values, are we happy that what we need to do to each of them is minus 25 and then half it? And if you guys want to start sharing your answers for that, that would be great. So theta, we need to do the value we had minus 25 over 2 and list out the different values we get for theta. And if you could check for me, very good. Yeah, so I think if we did it with 11.5 minus 25 over 2 minus 6.7, and then if we do the others, I believe we get minus 108.2, 71.7, and 173.3. Very well done if you got all of those. Now what we should notice is all of these are back in the original range of minus 180 to 180. So they're all valid. Now, if we'd have just taken off on the 11.5, the 25 and halved it, we would have not found all of the others. That's why we had to do the extend the range thing to make sure we collected all 4 answers before we transformed it back. So that was really actually quite important. Well done. Oh, because it's 2 theta plus 25, so 2 theta plus 25 is equal to all of those values. So for example, 2 theta plus 25 is 11.5. You would always minus first, then half it, because you'd have to half the 25 if you divided through fully by 2. Yeah, do we see that we're effectively solving like 4 equations of that, where you'd minus 25 and then divide by 2, but we've just got that scenario like 4 times. Does that answer that question? That was a good question, but do be careful with that. Is that okay? Yeah, you are solving effectively a little linear equation 4 times. Yeah, so although it's a transform, it is like a little equation. So some people say bid maths, some say bod maths. It's like the maths version of tomato. So if it's bod maths, it's order, meaning power, and I is index, but they mean the same thing. Right, so just a little indication of how confident you guys are. So if you just a little checkpoint for me, just a 1, 2, or a 3 to let me know. That would be great, and then we'll move on. Brilliant. So just a 1, 2, or a 3. Thank you. If you haven't already, let me know on there. And then we'll try and do some sort of slightly more involved questions. Great, lovely. Thanks, guys. Right. Now this next one, I think this exam style question is quite tricky. Yeah, okay. There's some tricky questions coming up, but I'm keen to push on. So I'll move this on, but thank you guys for letting me know in there. And do feel free to pause me and ask me the questions as we go for these slides, and we'll try and get through all of these. So it says sketch on a single diagram from minus 180 to 180. Oops. The 2 graphs of tan x and 4 cos x. So I would probably do the tan x one first. And I know kind of the key values you want to see on a graph would be every 90 degrees. Something quite crucial is happening. So try and do that a bit better. That would be 180. And that bit would be like that. So that's the tan graph. Now, if I do it in a different color, for example, the cos graph, if it's the graph of 4 cos x, how does that affect the graph? What does that do to the sketch? Because 0 is still there. What does it do as a graph transformation? It stretches it sort of in the vertical sense by a scale factor of 4. So the maximum is 4 and the minimum is -4. Very good. Yes, brilliant. It does stretch it. Superb. So what we've got here is it says there are has 2 roots and show A and B. Now this one is a bit tricky and I'm going to try and do this as kind of quickly as I can. Show alpha and beta on your sketch. So this actually does show that there are 2 roots to that equation because they cross in 2 places. Okay, so hopefully everyone can see that. So if we say that alpha is the first value and beta is the second value, okay, now hopefully that everyone's happy that that's where they cross. So that would be the solution to those 2 functions being equal to each other. Now this bit you might notice from the symmetry is sort of the same as this bit. This distance back from 180 is alpha. Does everyone see that? So whatever number this is where they first meet, they've not actually asked us to solve it. They've asked us to express beta in terms of alpha. So what we have is this distance back must be alpha. It must be the same distance as alpha is forward from 0. So because they've called them alpha and beta. Is everyone happy that these points are the solutions? If you're solving where 2 graphs meet graphically, it's where they cross each other. It's the intersection point of the 2 graphs. We don't know them. We're not asked to find them as a number. We're just asked to write them in terms of alpha and beta. Does that make sense that they would be the intersection? Yeah, be there and there. So what I would do, any equivalent of this would be fine, is that actually I know that alpha plus beta need to equal 180. So an equivalent of that sort of thing would do the trick for this, because that's beta forward and beta plus alpha must equal 180. Okay. So yeah, you can use all the different rules and try and put them together, but hopefully visually we can see like this beta value is how far from 0 to beta it is, and beta plus that same amount alpha would get you to 180. So there's different equations you could have formed. You could have used 90 and so on as well, but that is an example of an expression linking alpha and beta, or an equation linking alpha and beta. Okay, but I'm going to move on because I don't want to waste too much time with that one. Hope the main thing hopefully is you're happy with that sketch, that there are 2 clear solutions shown. The maximums and minimums are at 4 and -4. Right, now this one here, do feel free to work ahead of me and solve this. From 0 to 360 we're dealing with tan theta equals -3. So I'm going to draw the graph. Obviously feel free to use your calculator straight away. I'm going to do a little sketch so we're all happy with the interval we're looking at. That'll be 180. That'll be 270. And then let's try that again. That'll be 360. So 90, 180. Okay, right. And do feel free, as I said, to solve this. I'll do it by the TAN method, by the cast method as well, for those that would like that. I'm just a little bit conscious of the time here. So, so if we do tan inverse of -3, we get -72 as the principal value. And the good thing about tan is that like that first value comes out down here, -72. If we add that on to 90, take that back from 180, we'd get the value there of 108. And what's really good about the tan graph, and then we could just add 180 again, is tan repeats every 180 degrees. So on your cast diagram, SATC, tan is negative in here and here. And so this is negative 72. But if you add 180 to it, that'll get you your obtuse angle of 108. And then if you add on 180 again to that, that'll get you this value here of 288, which is exactly the same as 72 back from 360. So your answers for theta are 108 and 288 degrees. Right, I am a little bit mindful of the time because we've got a bit more to cover here, guys, the harder stuff. I'm going to maybe let you guys screenshot this and maybe come back to this one later on, and I can give you the answers if you've done it. It's a good exam style question. The way you'd start this off is start by minusing 1 from both sides, and then you've got it as minus 0.6, and then solve that. So if you guys want to make a note and try it and check your answers with me in the chat, I'll be able to clarify for you as we get there. So if you guys want to try this, as I said, the first step is to minus off, and then you're effectively solving minus 0.6. And then you're just being careful that you're solving it in that interval. So you're going to have to extend the domain. So give that a go. Let me know, and let's move on. So I'm going to look on rearranging the trig equations now. So this one is a good one to do. So for equations involving multiple trig functions, we can rearrange using trig identities. So for example, the two that we know, tan theta is sine over cos. Can anyone suggest what we would do here? So hopefully this is okay. So what we've got is 4 sine theta is cos theta, just doing a little bit of division. Then we would know that if I divide both sides by cos, I'd get 4 sine theta over cos theta is 3. And then divide both sides by 3, I'd get, by 4, sine theta over cos theta is 3/4. So therefore tan theta is 3/4. Now we just have it in one function. We know how to solve that. So if you solve for theta, inverse tan of 3/4 is 36.9 degrees. Then remember, tan repeats every 180. So you can add 180 on, and you'd get 36.9, and the other value would be 216.9. So we've used a trig identity there to get the same equation, but in terms of one trig function tan, and we've solved for that. And if you plugged both these values back in here and here, they would be equal. Okay, so you can still check your answer. Okay, right, I'm going to move on because I think a good one to do would be to solve one of the quadratic ones. So we can solve equations involving squared trig functions by either factorizing or using the quadratic formula, or some of you will know that your calculators do have. Yeah, so this one here, all I've done is I've divided by cos on both sides, and that gives me sine over cos, and then I've divided by 4. Okay, so if you divide that by 4, because 4 sine is like 4 over 1, so you then divide both sides by 4, so we've done a division. So factorizing or using the quadratic formula, or otherwise, however you would solve a quadratic. So someone kind of asked about this a bit earlier, I think, if there was sort of 2 scenarios to deal with. The way I would do is I would let x equal cos theta, and then this whole equation would become 2x squared plus 5x minus 3 is 0. And then what we do is we could actually factorize that. That does actually factorize 2x minus 1, x plus 3 equals 0. And now there's 2 solution sets here. either x is equal to a half or x is equal to -3. Everyone happy up to there? So that means that cos of theta, which is really x in disguise, is a half, or cos of theta equals -3. Cos of theta, that would say math error. That doesn't happen. The lowest cos can be is -1. So that leads to a dead end. You can't solve that. But cos of theta, we can now solve if it's equal to a half. And so if you do inverse cos of both sides, and we're looking for this interval between -180 and 180, we're going to get that theta is equal to, the principal value is 60. The other value it could be is -60. Okay. So that's how we solve that one. Right, is that okay? Does that make sense to everyone? Let me know if there's any bits I need to clarify. You may have seen this sort of substitution technique before, letting x equal it, so that you can write it as a quadratic, which you either factorize or otherwise you solve in another method that you're happy with. And then sometimes both give you potential solution sets. Cos theta equals -3 doesn't work, so you ignore that. But cos theta equals a half does, and that has two angles. So you carry on with that sort of train of thought. Good. So you reject the ones that don't work. So just a little indication of 1, 2, or 3 on how you feel with that stuff. And then what we'll do, we might try a couple more. And as I said, I'm a little bit conscious of the time, because I want to kind of wrap this up as well and talk to you, answer a few of the questions you guys had there throughout. But yeah, I think this is really good. And I think we're kind of getting a sense of how many things can build in quite quickly. Brilliant. And no worries if you're not 100%. This is a topic that does take a bit of mulling over and a lot of practice certainly as well. So what we'll do now is we'll try the next one. So let me just move this on. And any that we don't do, we could perhaps screenshot and you guys could try. But what I'll do is try and get through these next few now. So this one here is looking a bit kind of quadratic-y, but also it's a kind of annoying because they're not all in the same function. Any suggestions on what we can do with this? 2 sine squared x is equal to 1 plus cos x. I'm going to need to change something to get it all into one function. So I would suggest, think about your identities. What could we change here? Well, we know that sine squared plus cos squared excellent is 1. So 1 minus cos squared is sine squared. So I can replace sine squared with 1 minus cos squared x. Brilliant. So we're just, and then it's all in terms of one thing. So if I expand that, and do let me know if you're not happy with that, but this is the sort of thing we need to practice and be able to spot, you know, quite quickly. Yeah, no problem. Absolutely right. Then I don't particularly like negative quadratics, so I might bring it to the other side of 0, add 2 cos squared across, minus 2 across, and I'd get 2 cos squared x, add cos x, minus 1 equals 0. And I could let that equal y and try and factorize it, but it would factorize as 2 cos x plus 1. So here cos x equals to a half and cos x equals to minus 1, which is actually valid as well. So if you do your principal values for each of them, you get cos, inverse cos of half is 60. And they're actually your only solutions because we're only looking up to 180 degrees. So we get both of those. And you could put them back in the original to check. Okay, is that okay, guys? Does that make sense? So there are solutions there. Now, again, you could have used a substitution to help you factorize it or equivalent, but I've gone through that sort of fairly quickly. But they're the sort of steps you definitely want to be able to show. Okay. And well done if you did spot that you had to do that with the identity. So very well done. I'm going to push on. So the next one here now, again, some of you were asking earlier about addition formula and double angle. You don't need to do that for this because again, what we can do here is we can deal with, okay, also remember it's 2x. So if if x is between 0 and 180, 2x, we need to extend the search around to 360. Now here, sine of 2x is equal to like -1 lot of cos 2x. So if I divide both sides by cos 2x, I get, I'm going to write this explicitly, sine 2x over cos of 2x is equal to -1. So tan 2x is equal to -1. So you could find your principal value on the calculator. So 2x is equal to -45 degrees. Remember, tan repeats every 180. So you can add 180 to each of those, or to that value, and you're going to get 135. And if you add 180 again, you're going to get 315. And they're your solutions for 2x. So what I need to do, that's out of range, is half both of those. So x is equal to 67.5. Yeah, so we use trig equations a lot of the time. A lot of the time to solve these. Apologies if the mic cut out there. And that's what we've done for each of these harder ones. So we've had to use tan from trig identities. Absolutely. So what I'll do is, if you guys want to make a note of this one, I'll quickly talk through how you do this. So this one is actually factorized for you. Now, the possible values of tan is that from here, tan theta could equal -1, would solve that. You wouldn't use double angle for that one because they were both in terms of 2 theta anyway. So that would be like, it would make it more complicated, I would say. So tan theta is -1, solving that bracket. And in a similar way, you could set that bracket equal to 0 and solve for tan, like we've been doing by identities, because you'd get tan squared theta equals 3, which means that tan theta is ±√3. And then from here, you would solve with each of these different solution sets. There's sort of 3 ways of getting your answer. So either tan theta equals -1, or this would lead us to tan squared theta equals 3. So tan theta equals ±√3. And then you guys could carry on and solve from there and give that a try. There are 3 potential answers for this one, and they all work out quite nice. So does everyone see what I did for this? I know I've sped up a little bit there. I'm just kind of mindful of the other bits I want to talk to you guys about. But because this is fully factorized and equal to 0, are we happy that we can say, when is that bracket equal to 0? Tan theta equals -1 if you rearrange, because tan theta +1 would have to equal 0. So tan theta equals -1. Or here, you'd have sine squared theta -3 cos squared theta equals 0. So if I rearrange that, sine squared theta equals 3 cos squared theta. Divide by that, and I get sine squared theta over cos squared theta equals 3. So tan squared theta equals 3. So tan theta equals ±√3. And then that's where my 3 different solution sets come from. So you'd have to solve for this, you'd have to solve for tan theta is √3, and you'd have to solve for tan theta is -√3. Okay, so good. I'm glad we clarified that, and apologies for rushing that a little bit. But these are good ones to look over and practice, these ones that bring in the identities. And then once you've tidied it up, just become normal trig solving, as this is useful for both year 12 and 13. So we've done a lot there. What I did just want to mention, because I know we're reaching exam season now, well done for everyone for using your time on the Sunday to work through more maths and look through the trig. If you are approaching exams, both year 12 and 13, as we kind of approach April and May. I did just want to mention the A-level seminars. Is anyone signed up for this? I'm kind of interested to know. If not, I do just want to talk about this quickly and show you how to sign up or register your interest, as I believe there are still places. We're going to go through the whole A-level course, pure mechanics and stats, in light of the advanced information at the seminars in in April. So what we've got is, and I can't wait. I think it's going to be a brilliant couple of days. And as I kind of mentioned before, and you've probably seen on some of these other web classes on YouTube, there's going to be some really nice resources that help you kind of work through the whole course and kind of really meticulously tease out each bit. And there'll be additional support on the day as well. So there'll be year 12 content covered on one day, year 13 on the other. We will still be running the YouTube sessions as well. So do keep looking at those each week. But as I said, this will be a really kind of comprehensive look at the whole A-level with the opportunity to ask questions and really tease out stuff that is going to come up. So the dates are there. So the 6th and 7th of April for the maths ones for year 12 and 13. And they will be sort of live streaming them as well for people that can't attend in person. So you can sign up for that option as well. And what I'll do is, if I share, hopefully be able to share the Snap Revise website so you guys can see it. Let's have a little look. So let's have a little look. So you can book your place there on the Snap Revise site. So the seminars and crash courses are there, and you can go to book a seminar. So you've got the option to sign up for the different days, and also whether it's in person or the kind of live stream side of it as well. So the courses are there for you to have a little look at. So check them out on the site and do find out a bit more, because we're going to be doing that over the Easter break. And yeah, there's quite a few really good resources that will help you with that. I'm really excited to be part of that and be delivering that this year. I think it's such a unique position we're in this year, with the exams coming back and also having a bit of information about them to work with. So these seminars, we've got, as you can see, the kind of general presentation and the layout of the notes and the examples are very clear, but we're going to go through and really break down the different exam style questions in light of what we're kind of aware of will come up. So these courses have been really tailored this year, kind of making the most of the information we have. It'd be lovely to see you guys at attending some of those sessions if you can, or via live stream. I think it's the unique opportunity to be able to ask the questions in that live setup that will be hopefully really useful for you all. So if you can, and if you are joining, it'd be lovely to see you there. I did want to just take this time at the end to mention it because it's coming up quite soon. And I know a lot of you are gearing up for revision, just based purely on how you're working today and the kind of mindset we're in this term as we're approaching the final summer term of school. So yeah, really well done. And thank you so much to everyone today for taking part so well with that trig content. It is something we need to be really prepared for both years. But yeah, as I said, if you haven't already, do check out the crash course seminar stuff on the Snap Revise website. And it would be lovely to see you there. And also the future YouTube sessions will hopefully see you out as well. But yeah, check the resources out, because as I said, they've been really tailored towards this new information. And yeah, I know how useful that can be, especially if you're kind of in the situation of trying to kind of make the most of all the information you've been given. I know it's a stressful time for everyone studying at the moment, whether in any kind of year. So all the kind of help and support will be there in person and online remotely as well on those days. So it'd be really nice to kind of help you through as we reached kind of May and exam season this year. But really well done, and hopefully see you all at a session soon either way. Thank you again for all the answers and questions and comments as we work through this today. Have a good week, keep well, and look forward to speaking to you guys soon. Well done. Thanks again, and take care, guys. That's great. Thanks. See you later. Well done. No worries. Thanks, guys.